So in this unit, we're looking at eigenvalues and eigenvectors. And 5.1, we were looking at eigenvalues, eigenvectors. We really didn't know how to find an eigenvalue, though. Wasn't a very clear process. We really didn't find eigenvalues. So basically, we had some eigenvalues. We gave you some eigenvalues, and we were able to find the eigenvectors, right, by looking at certain homogeneous equations of the form a minus lambda I times the vector x equals the 0 vector. Those homogeneous equations, they would give us eigenvectors. But how do we find the eigenvalues? Let's remember what an eigenvalue is. So lambda, which is a scalar, is an eigenvalue of a matrix A. Has to be a square matrix, provided what happens? A times some non-zero vector x gives you lambda x. This is for some non-zero vector x, and Rn. So essentially what happens is you multiply that non-zero vector by A, and it would stretch it out possibly. It keeps the same direction, the vector. It stretches it out, it shrinks it down, or it reverts it in an opposite direction and negative orientation. So how do we find these things called eigenvalues? The eigenvalue here, the lambda, is basically your stretching factor or your shrinking factor, or if it's negative, your flipping factor. How do we find these? We're going to use something called the characteristic equation. The characteristic equation, we want to introduce the characteristic equation. This is the easy way, or the efficient way, to find eigenvalues of a matrix. So we want to give a definition. What is a characteristic equation? We'll start off by defining what's called a characteristic polynomial definition. So let's say I have an n by n matrix. Let A be an n by n matrix we want to define the characteristic polynomial first. The characteristic polynomial that's what we're defining. It's denoted, here's the notation, P sub A of x, it's actually a function of x, it's a polynomial, is defined by the following. P sub A of x is defined to be equal to the determinant of the following matrix, A minus x times I. So x is just a real variable. It's a variable that can take on real values. All right, so that's what the characteristic polynomial is. It's the determinant of A minus xi. Determinant of A minus xi. I'm going to put in there, just so we know we're dealing with an n by n identity matrix. So here's another definition. What is the characteristic equation? So we have a polynomial, a characteristic equation. The characteristic equation associated with an n by n matrix A is precisely the equation P sub A of x equal to 0. So it's when you take the characteristic polynomial and set it equal to 0. So basically you're finding the zeros of the characteristic polynomial, the roots of the characteristic polynomial, you could say. So that's what the characteristic equation for n by n matrices. Is your characteristic polynomial set equal to 0? All right. All right, so here is an important result, super important result, theorem. This is how you're actually going to find your eigenvalues for your matrix. So let A be an n by n matrix a scalar called lambda, so lambda, a real number, is an eigenvalue if and only if the following happens. P A of lambda equals 0. So what are we saying? We're saying you have a eigenvalue of a matrix. I should have said of A here, right? I should have said of A. Of A. Let me write of A. Lambda is an eigenvalue of A if and only if and only if lambda satisfies the characteristic equation. So basically, when you take lambda and you plug it in for the x variable, it gives you 0. It gives you 0, yeah. So if lambda satisfies the characteristic equation. So you take lambda, plug it into the characteristic polynomial, and you get 0. Okay, we can prove that. That's really easy to prove. So you're going to see this construction, this construction that we're going to do. You've seen it already in 5.1. So we're going to do it again. It shows up a lot. It's a really important construction for eigenvalues. Okay, so let A be an n by n matrix. Let A be an n by n matrix. So lambda, which is a real number, is an eigenvalue of A. What does that mean? Well, that's equivalent to saying, use the if and only if arrow, equivalent to saying A times some non-zero vector x equals lambda x. This is for some non-zero vector x. Now, we've done this construction already. We're going to do it again. We're going to leave the lambda alone. We're going to take the x on the right-hand side. And we know that x is the same thing as the identity matrix times x, right? Identity matrix times x gives you x. So we're going to replace that blue x with the identity matrix times x. Okay. And all along we have to remember that this x vector is non-zero. This stays through all the way. Right, now what I'm going to do, I'm going to subtract my right-hand side from my equation. This is equivalent to ax minus lambda in x. So when we subtract the right-hand side, on the right-hand side we're going to end up with the 0 vector, right? 0 vector, that's just a vector. And remember, x is a non-zero vector. We need to state this all the way through for some solution of vector x that's not 0. Okay, so notice here we have an x here on the right on each of these terms, so to speak. I have ax and minus lambda in times x. So we have a property, a distributive property essentially, for matrix vector multiplication. Distributive property, where we can essentially factor out the x on the right. This is the reverse of the distributive property. Factoring is the reverse of the distributive property. In parentheses, we're going to have what? A minus lambda in. On the right-hand side, we have the 0 vector. And we have to keep in mind that this x is not 0. It's a non-zero vector. So what do we have now? We have basically a homogeneous equation, right? Homogeneous matrix vector equation. You could say a homogeneous linear system. right? So we have this A minus lambda in, that's our matrix. X is our solution vector, equals 0. So the right-hand side is 0, so it's a homogeneous situation. Now notice that your solution vector, x, is a non-trivial solution, right? It's a non-zero vector solution. So this means, remember, that means that the matrix is singular. If you have a non-trivial solution to the homogeneous equation, that means A minus lambda in is singular. So it's not invertible. It's singular. Remember, a matrix is singular, which means non-invertible, if and only if the associated matrix vector homogeneous equation has a non-trivial solution. Also remember, if something is singular, if a matrix is singular, that means the determinant of that matrix is 0. So the determinant of A minus lambda in has to be 0. But wait a second, what's another name for the determinant of A minus lambda in? This is just a fancy name for determinant of A minus lambda in. That's the characteristic polynomial of A evaluated at what? Lambda, right? Evaluated at lambda, right? So rather than x, we just have a lambda plugged in, a number lambda plugged in place of the real variable x. So that's the proof. So that's what we wanted to show, right? We wanted to show that lambda is an eigenvalue of A, right? Lambda is an eigenvalue of A, if and only if you take the characteristic polynomial and evaluate it at lambda, you get 0. And that's what we've done, right? We've shown lambda is an eigenvalue of A, if and only if the characteristic polynomial evaluated at lambda gives you 0. All right, so that's incredibly useful right there. This allows us to find eigenvalues of matrices really efficiently. Let's see if we can do some of this stuff. Find all real eigenvalues. So we're not going to do any complex eigenvalues. You can have complex numbers of A. We're only going to find the real ones. We're not going to worry about any complex numbers. All right, so number 1. Here's our first matrix. 2, 2, 7, negative 3. So we have to deal with square matrices. Always it's going to be square matrices when you're talking about eigenvalues, eigenvectors. So we're not going to find any eigenvectors. We already found those last time. We know how to find eigenvectors. But eigenvalues, this is the thing we're going to learn today. All right, so let's say lambda is an eigenvalue of A. That's the same as saying what? The characteristic polynomial evaluated at lambda equals 0, right? Determinant of A minus lambda I, that's the characteristic polynomial evaluated at lambda, right? We're just plugging in, instead of an x, we're plugging in a lambda for x. That should be 0. Right, this is the characteristic polynomial right here, this guy, determinant of A minus lambda I, that's called the characteristic polynomial. All right, so let's actually write out the details on this first one. In the future, I'm not going to write out so many details. So this is the determinant of, so A is going to be what? 2, 2, 7, negative 3. And then we're going to subtract lambda I. So you think about the identity, it has what? 1's down the main diagonal. But instead of having 1's down the main diagonal, when you take lambda I, you're going to have what? Lambda's down the diagonal, and 0's everywhere else. And this is going to be equal to 0. So in reality, what's going to happen, you're going to go back to your A matrix, and you're going to subtract lambda from the main diagonal. So you're going to have what? 2 minus lambda, and negative 3 minus lambda. And all the other entries are going to stay the same, right? You're going to have 7 up here. That's not going to change. 2 right here. That's not going to change. So in the future, we're going to kind of skip past that second step. We'll just go from the first step to this third step here, you could say. So you just have to remember to subtract lambdas from the diagonals of A, basically. All right, so now we're ready to compute the determinant. Remember how to compute the determinant of a 2 by 2 matrix? You're going to take the entries along the descending diagonal and multiply them. So you're going to have, what, 2 minus lambda times negative 3 minus lambda. And then minus, and then you're going to take the entries up the ascending diagonal, 2 times 7. And that's going to be equal to 0. So I'm showing more steps than I normally would. All right, so that's equivalent to. Let's FOIL this out. We're going to have what? Negative 6 minus 2 lambda plus 3 lambda plus lambda squared. And then minus 14. That's equal to 0. So we clean this up, right? We put the lambda squared first. We combine the lambda terms. We're going to get, what, plus lambda. Then we combine the constants. Negative 6 and negative 14 is what? Negative 20. That's all equal to 0. And from here, you can just solve that equation. This was the determinant of a minus lambda I. We can factor this, right? I have a lambda times a lambda, get lambda squared. And then you got to find two numbers that multiply to give you negative 20 and add to give you 1 right here. It's going to be what? Positive 5, negative 4, right? They multiply to give you negative 20, add to give you 1. So there are going to be two distinct roots here. Two distinct roots. So this is equivalent to what? Lambda gives you negative 5. That's one of your eigenvalues, and the other one's lambda gives you 4. Now, it turns out that the multiplicity of negative 5 is 1, right, because it only shows up one time. So I'm going to go ahead and state that the multiplicity is 1. That's called the algebraic multiplicity. And the algebraic multiplicity of 4 is going to be 1 because it only shows up one time. I'm going to just state that below. It's something we're going to have to get used to doing. So these are the two eigenvalues of this particular matrix. So the maximum number of eigenvalues you can have for a 2 by 2 is 2. You can have up to 2 eigenvalues for a 2 by 2 matrix. All right, let's do another example. One more example. So here I have a matrix. This one's going to be a 3 by 3. 3, 0, 0, 2, 1, 0, and then the third column, negative 1, 4, negative 8. So we want to find the eigenvalue, so we're going to say what? Lambda is an eigenvalue of A. Precisely when, if and only if. Determinant of A minus lambda I. A minus lambda I. This is actually I3. If you want to write I3, you can. Some people just write I. I'm going to go ahead and put I3 right there. Equals 0. So I'm writing that right now. So you don't have to write that second step every time, but I'm writing it right now just because initially you want to kind of get used to writing that. So you remember that. All right, so actually what happens is the main diagonal gets a lambda subtracted, right? You get 3 minus lambda, 1 minus lambda, negative 8 minus lambda. And all the other entries basically stay the same, right? You get 2, negative 1, 4, 0, 0, 0. So the diagonal entries change on the A because you're subtracting a diagonal of lambda, basically. Now, when we take the determinant of this one, it's actually a very nice determinant to compute. We know from determinants, right? We did determinants, about a month or so back. When you have a triangular matrix, upper triangular, lower triangular, whatever, it's just the product of the main diagonal, the determinant is. So we have 3 minus lambda times 1 minus lambda times negative 8 minus lambda. That is the determinant of this matrix. We don't have to do any other work than that as far as calculating the determinant because we have an upper triangular matrix. So this is equivalent to saying that lambda is equal to 3, lambda is equal to 1, or lambda is equal to negative 8. So those are our three. We have distinct eigenvalues, 3 distinct eigenvalues. I'm going to write the multiplicity. Multiplicity of 3 is 1. That's called the algebraic multiplicity. multiplicity of 1 is 1 and only shows up once, and the multiplicity of negative 8 is 1. So they'll have algebraic multiplicity 1. Meaning they show up once. All right, I think maybe we'll stop there and we'll do another video. So this is an introduction to finding eigenvalues very efficiently using this thing called the characteristic polynomial in the characteristic equation.